This lesson is going to be about creating Lewis structures, drawing structural formulas, and determining the structural shape. And we're going to do several examples, including those with double and triple bonds. So the first example I'd like to go through is CH4. So CH4 gives you one carbon with 4 hydrogens. To start off with the Lewis structure, we recognize that the carbon has 4 valence electrons, and hydrogen, if I look at the periodic table, has 1. All right, so that tells us because I have 4 valence electrons, each have a single electron, that these are the locations where bonding can happen. It can happen where there's only one. Once you have a pair, that means there's no longer any bonding allowed because it is full already. So in this case, you have this being the Lewis structure. If I draw the structural formula, I simply replace those shared electrons from the different atoms and replace them with dashes. So what that looks like, if I were to do a toothpick model of it, is that I have carbon in the center. I have my toothpicks, which we were using, representing these electron pairs. And from these electron pairs, I have hydrogen. We call this a tetrahedral shape. And this is the basic shape of all single bonded molecules because it allows the electrons to be as far away from each other as possible. Electrons far away, okay? And keep in mind that is because they all have that negative charge, so they repel each other. We call this the tetrahedral shape. So to get a sense of what that actually looks like, if I were to do a particle model, it would look like this. You notice here we've got the top shape, then we have the extensions going out to here to hopefully look like something that is a tetrahedral shape. I know that that makes it a little bit hard to see, but it is like that toothpick example that we had in class. So let's try another one. Let's do NH3. All right, so this is NH3. I want to start off with the Lewis structure. I recognize that there are 5 valence electrons in the nitrogen, on the electron shell, last valence electron shell, and this tells me there are 3 locations where bonding can happen, and I just happen to have 3 hydrogens. So I'm going to bond the 3 hydrogens in their respective places. All right, I have one lone pair over here, and so my structural formula should look like this. If I want to include my lone pair, I can put 2 dots here. It's not necessary. Now, having said that though, if I have nitrogen being my central atom, recognize that I still have those 3 electron pairs, those 4 electron pairs extending out. So I should still have my 4 toothpicks sticking out. It's just that now here, there's no atom attached to it. I only have atoms attached to the bottom, and these are my hydrogen atoms. So it's still the same shape with the tetrahedral, but this time I don't have anything attached. So I'm going to just be looking at these here, and you'll notice that these sort of make a pyramid shape, and that's why it's called a pyramid. And to take a look at what that pyramid looks like, this doesn't do a very good job of showing that, but it should actually be a 3-dimensional model. I'm looking from top down that sort of looks like that, okay? So this being the front right here. And we call that a, I know they call it trigonal planar, but we call it a pyramid shape for our sake. All right, so now let's try another one. Let's try H2O. All right, here we have oxygen being our central atom. We have oxygen, which has 6 valence electrons. I then go into adding my hydrogens. My hydrogens are right over here because those are those single ones. And so when I draw this structural formula, it should look like this. So it's the same idea. I still have four pairs of electrons. So when I draw oxygen here, I still need to have four toothpicks sticking out as far away from each other as before. So I still have that tetrahedral shape. But in this case, you notice that there's nothing attached on the top and nothing attached on the bottom, but you do have a hydrogen attached here and a hydrogen attached here, and you notice that it gives you sort of a bent shape. And so for that reason, we call this bent. The last one I want to go through is fluorine. So fluorine, or let's do hydrogen, even better, H2. So H2 is a great example where you have, in this case, one hydrogen and another hydrogen, both having one electron that they can share, and so it makes a bond that looks like this. So in this bond, you'll notice that there is no valence electrons, no electron pairs over here, none here, none here, none here. They simply have one here, and so these are attached to each other with no other toothpicks in a very linear shape. Okay, so whenever you see any sort of attachment where it's just two attached to each other, they will always form a linear shape. So let's review that in terms of our shapes over here. So you notice over here, carbon dioxide is a linear shape also, but if I were to remove that, that shows how you have a linear shape. And here again, I have that water clearly bent, right? So now let's make this a little bit more complex in terms of introducing the idea of a double bond. So in one of your problems, you have carbon dioxide. So you have in this one, CO2. For CO2, you have carbon as a center, and you have two oxygens over here. All right. And then you notice that you have these two lines. These two lines show what we call double bonds. Now, what is a double bond? Let's take a look at it as a Lewis structure. So carbon, again, is our central atom, and we're going to now add some oxygens. So for oxygen, I know that there are 6 electrons, so I just sort of paint them on there. Okay, so with that said, you notice that here I have a single electron, there I have a single electron, here I have one too, and there I have one also. What happens is that these single electrons move over, so this red one from oxygen will scooch over and end up over here. This one, so this is no longer here. This blue one will move over here. And you have now a double bond. So you notice that these now are bonded together. So that gets rid of this one as well. Over here you have a single electron, and over here you have a single electron. Same thing happens. So you have this blue one, this electron shifting over to this side, and you have this red one shifting over to this side. Okay? And so again you have another double bond, and that's where you get this structure. And as we saw, this has a linear shape. So let's try another one. How about C2H4? I'm going to have you work through this one by yourself and then check your answer. So give it a try. So hopefully you have set up your Lewis structure to look like this. We're going to add 4 hydrogen. Oops. Let's make that blue. We're going to add 4 hydrogen bonds. And I can tell that they're changing colors, but that's fine. We'll deal with it. Okay, so we have a lone electron here. We have a lone electron here. So in this case, those electrons move over, so you no longer have this one. This electron moves over, you no longer have this one. And you have a structural formula that looks like this. So just to review, it's because I had these single, there we go, because I had these single electrons, they can shift over and bond with each other. And it makes no difference that it's two of the same atom, as long as it's two atoms that are bonding. So let's try the last one, which is C2H2. We have, in this one, I'm going to also have you stop the video and give it a try, and then you can check your answer. So for this one, I have carbon, all right, and I have two hydrogens. Move that, two hydrogens. So the hydrogen, I'm going to attach one here and attach one to the other side. In this case, I have a full pair over here, and I have a bond over here, right, from the carbon. But I have two electrons on this side that are by themselves and two that are on this side. And I simply move them over so that this one goes here, this one goes here. That's another bond. And now I'm going to take this one over here and this lone one over here to create the third bond. So this one has a structural formula that looks like this. And we call this here not a double bond, but a triple bond. And that ends our lesson.